So now the question is, what is the basic principle of encoding spatial information? We have, during detection, in the presence of a gradient, we have a spatially varying resonance frequency. So the Z field is equals to B0 plus gamma gx times x. And so if we plot this as a function of x, we have the magnetic field here and here, it increases, etc. So that's gamma bz over x. Our transverse magnetization now will precess, it will be given by the transverse magnetization at position x times e to the I gamma bz times t. So this is in general terms, this is how this is written here. We have the B0 term and we have the gradient term. Now what we'll do is we'll put ourselves into the rotating frame to describe that so that we don't need to consider the gamma B0. Remember, gamma B0 is much bigger than gamma Gx times x. So we have now just a magnetic field that varies with x. So it's a z component. So now we can write the precession of the transverse magnetization is given by the transverse magnetization at position x times e to the I gamma gx times time. So if we look here at this position, our magnetization vector will precess here with a certain precessional frequency. If we go at this position, the magnetic field is stronger, so here it's precessing faster. And finally, at this position, we have even stronger magnetic field, and here the magnetization precesses faster. So this is what we are detecting. We have different precessional frequencies, and they depend on the position of the magnetization. Now the signal that one detects is given by the sum of all precessing magnetization. So what we now have to do is, to get the signal as a function of time, we have to integrate over the object here along x, the magnetization at time 0 at a position x, times the evolution term here, so that's the phase evolution, and here we're basically saying that the real part is, for example, corresponds to the x component of the transverse magnetization and the imaginary, the y component. So we'll do this integration over position. So what does this equation resemble? Have you seen a similar equation already? Does it ring a bell? How about this equation? Does that ring a bell? You have most likely come across this type of equation, and that's an inverse Fourier transform. Essentially looking at a signal that we are detecting is the inverse Fourier transform of the magnetization as a function of frequency. And here frequency and position, they are linked through this equation, linearly linked to that. So this is a Fourier transformation of the object's magnetization that we detect. So we can rewrite this equation that we have here. I will write it as S of k, which is proportional to the integral over the object, magnetization again at time 0, times e to the I kx dx. So, and here we're using the term k for k-space. This is the conjugate or pair variable to position x. So here they are, x and k are linked through Fourier transformation. They are the Fourier pair, like in this example, omega and t are the Fourier pair. So if we take now the Fourier transformation of the signal that we record with time, or we can also say that we record as a function of k-space, this gives us the magnetization along x. If we write this now for a 2D object, then the magnetization at a given position x that we observe, so we obtain Fourier transformation of this, we obtain m of x, and this m of x, if we look at a two-dimensional object, is then given by the integral of the magnetization in x and y along y, because we cannot distinguish in the y direction the position if we apply a gradient along x. Now this equation, does that look familiar? You have certainly seen it in the first part of this course. We have introduced it for computed tomography, and this is a radon transform. So in principle, I could stop here and say, well, once, like I've said before, once we see that the signal corresponds to that of a radon transform, we know we can reconstruct an image with back projection. So in principle, the reconstruction can be done here as in computed tomography. However, this is not the general case, and I will not stop here the lecture for this week, and we will go into the way that the images are reconstructed. So first I want to come with a 1D example, and we'll take here the example of two point-like objects. These could be capillaries, so they have very small dimension. Here they are. We'll give the position along X here, and without encoding, that is the magnetic field, which is plotted here, is constant in position. We have a constant magnetic field in position, and we will record a nice free induction decay, decaying signal. The frequency is the Larmor frequency, and the decay is T2. Now, if we apply a coding, then the magnetic field varies linearly with space, and we'll take here the encoding along X. So we have applied a gradient along X, so it's a spatially varying magnetic field, and this produces now a oscillation of two frequencies. We have two capillaries, two positions. We'll assume they're point-like, so they're two very well-defined frequencies. This gives a beating pattern of two frequencies, and that typically looks like this. Now, if you imagine you have a more complex object, it is not so obvious just to see from the signal that's recorded what is being observed. So what is done now is we apply the Fourier transformation. That is, we decompose the signal into its frequency components. That's what Fourier transformation does for you. So we'll take the signal, Fourier transform it. Here we get a single resonance. We have a constant magnetic field. We have no information on the position. And in the presence of a spatially varying magnetic field, we're getting two peaks, two resonance positions according to two frequencies according to the position of these two capillaries in this example. And so these projections that we obtain, like I've said before, we could in principle reconstruct the image using back projection. And this was indeed in the very first experiment done by Paul Otterberg, a physical chemist, in the early 70s. This is actually how he produced the first images. He used MRI with back projection. The other person that is noteworthy to mention also in the early 70s took a different approach. That was a physicist, Sir Peter Mansfield. And Paul Otterberg and Sir Peter Mansfield, they shared the Nobel Prize in Physiology and Medicine in 2003 for their groundbreaking work in making imaging possible with magnetic resonance.